Okay, so yesterday we did a very, very brief intro to some Chem 30 stuff. Let me just re-talk about some of the things I said yesterday. In my opinion, the way that we kind of structure our chemistry, grade 10 is really just baby steps. We teach you how to name stuff. Right? Like, to be honest, that's not really doing chemistry yet. It's just, can you name silver nitrate? If I tell you that I give you the formula CuCl2, do you instinctively know that that's copper 2 chloride? Right? Like, eventually, those are important skills, don't get me wrong, but grade 10 chemistry is really just naming stuff. It's not actually chemistry yet. Does that make sense? And in grade 11, the main units in grade 11, really the focus of those is, can you do some basic calculations involving chemistry? Most of them involve things like being able to balance an equation, being able to do moles and mass and liters type calculations. And again, not that I want to tell you that what you've done up till now isn't really chemistry, but it's not like the fun, cool applications of chemistry. Okay? And that's where I think this is where like chemistry we start to actually becoming it's useful. Okay? So the main units we're going to do, the first one we're talking about is on thermochemistry. That's basically the study of how energy, heat, is involved in alchemical reactions, endo and exothermic reactions. Our second unit is electrochemistry, the study about how electricity, the flow of electrons, interrelates with chemistry. I mentioned yesterday one of the probably most revolutionary technologies to come from chemistry would be the battery. It's the idea that we can use electricity to run your iPod for hours on end, right? And not only that, but nowadays we have devices that can recharge. It used to be that you had to put AA's into everything, and then once the AA's died, then you had to go buy a new set of AA's, right? You just plug your iPhone, and most of you plug your iPhones into the receptacles right here, and you don't even think anything of it, right? That's chemistry. Like that technology behind that is a useful application of chem. The third unit's on organic chemistry. I would say that unit is, the main focuses are things like oil and gas industry, as well as anything synthetic. I talked about, I think, medicines the other day. The idea that, if you go to, Shoppers Drug Mart and buy some ibuprofen because you have a headache, that's a synthetically created in a lab medicine, right? That's chemistry, though. Does that make sense? The last unit I didn't talk about yesterday. The last unit is actually, it comes back to acids and bases again. Which is kind of where I like to start when I teach you guys Chem 20. And so back to hydrogen and hydroxides and pHs and POHs. And it kind of continues that. For you guys that were in my grade 11 class just a couple, weeks ago, one of the things we would have learned back in grade 11, maybe you guys in grade 12 still remember this, is the idea of trying to be able to look at a compound on paper, like say HCl, and be able to tell whether it's an acid or a base. And one of the things that we learned to do was say add it to water. And if you add it to water, if you can make hydronium plus something logical, this proves that it's an acid. Do you guys remember this concept from a little while back? There was an unsolved problem that we never quite got to, though. It was the problem of, what if on paper I can write something both ways? Let me give you an example. Let's say it's NaHCO3. NaHCO3 at its core is ionic. The reason it's ionic is because here's a metal and here's a non-metal. Or if you want to talk about electronegativity differences, this guy has a very low electronegativity, and these guys right here are higher. So the first thing it would do is it would dissociate into this. Do either of those prove something's an acid or a base? No. So what I would have shown you how to do is you take this guy down here to like the next step. This guy here is now something molecular, so add it to water. And I can actually write this two different ways. I can take this hydrogen right here and throw the hydrogen on water to make it hydronium, which would give you CO3 2 negative. There, I proved it's an acid. The other possibility is valid, though. I could take a hydrogen off of water, and it would leave a hydroxide, and it would become H2CO3. H2CO3 is not polyatomic, but it is a valid molecule. And so one of the issues you should have, hopefully you recall this, that we came across at some point in grade 11, is that this compound right here, I would have said we can prove that it's both an acid and a base. But is it actually both an acid or a base? The answer is no, it is one or the other. And so that's what our last unit helps to focus on, is try to help solve a little more of the mysteries of how acids and bases work. Does anybody actually know what we call NaHCO3, by the way? Anybody aware of what it is? Okay, what would its chemical name be based on how we name this? Na would make it. And then anybody know what an HCO3 is called? It's in your data book.
Is it carbonate?
Not carbonate, it's close though. It's called a sodium hydrogen carbonate. Is there something in brackets next to the hydrogen carbonate, or did they take that out of this data book? Okay. They used to put in brackets. You guys maybe even want to write this one in, just because it may come up. An HCO3 has been given a common name. It's called a bicarbonate. HCO3 negative. Hydrogen carbonate works, but sometimes they also call it a bicarbonate. So this thing sometimes is called by the name sodium bicarbonate. I guarantee you guys have seen this compound before, not just in my lab. It's baking soda. Anybody ever heard that before? Sodium bicarbonate is baking soda. It's a base, yeah. Yeah. If you ever seen like a lab where you take like vinegar and baking soda, you put it in a pop can, you shake it up, you put a balloon over top, or something simple like that. So, long story short, I'm getting way off topic, but you guys probably know this by now. I do that. Our last unit is going to help us try to explain a little bit better how acids and bases work, because on paper, I was able to show you that sodium bicarbonate could be an acid or a base. But the truth is that this reaction, the top one right here, does not actually occur. It occurs in a less proportion, actually, than the bottom one here. This is the predominant reaction. And so that's our last unit, trying to explain how that works. Does that make sense? Anyways, I think the whole reason I still had to start this line of thought was the topics that we do in Chem 30 are a lot more applicable, I think. Would be a good word to use. Maybe not applicable because you use this every day, but applicable in like the scientists who use these principles have made stuff that you use every day, right? I mean, if you just added up all the things in this room here that are based on, someone in chemistry had a great idea and managed to turn it into a piece of technology. I mean, the plastics that we use on the top of the table, that laminate kind of sheen on top of it, that's a chemistry thing, right? Being able to coat the sink right here, that's probably like some sort of chromium. Right? Being able to electroplate something, that's chemistry. So, okay, I'm getting off topic. So let's focus on thermochem for a little bit again then. Thermochem, the main concept is that all reactions involve the flow of energy. If it requires energy, something requires energy, it's good job, yeah, endothermic. And if something produces energy, then it's exothermic. I gave an example yesterday of warfare has really been changed by chemists' knowledge of how things work. I mean, whoever discovered gunpowder, I think it's attributed to Chinese culture from thousands of years ago. But I mean, even if you work forward into, I mentioned Alfred Nobel and dynamite and the atomic bomb, C4 explosives, right? I mean, most of those are very powerful exothermic reactions producing a massive amount of heat, right? What my goal today now is to talk about how to quantify that. Do you guys remember the terms qualitative and quantitative? Okay, so let's talk through them. A qualitative observation is qualities, basically. A quality might be that it burns yellow. That's a quality. A quality might be that it's hot. A quantity might be that it burns at 5,002 degrees Kelvin. What made it a quantity? Yeah, I attach a number to it. Does that make sense? So quantitative measurements would be attaching a number to it. So imagine that, I don't know, you're Alfred Nobel and you just discovered that dynamite really packs a punch when it blows up. But how do I quantify it? How do I attach a number to it? How do I say, well, dynamite is 10 times more explosive than gunpowder? Does that make sense? We want to try to find a way to attach a number to something. So herein poses the problem. How do we Does that make sense? So first thing I want to add then, I guess this is the sort of stuff you want to write in the margins. Let's go with this here. How do we measure energy? Anybody know? What's the unit of measurement? The unit of measurement is joules. Yeah. Sometimes we measure in kilojoules. Now, one of the issues with energy, if you've taken physics before, I know some of you I taught physics before, so let me just give everybody a rundown on energy, though. In terms of energy, energy is something considered to be scalar. Does anybody know what that word means versus vector?
It doesn't have a direction.
That's good, yeah. Basically, it means it's directionless. If I were to throw this eraser, and I talked about its velocity has a direction because it went that way. But energy is a bit different. Energy is scalar in that it permeates outwards in all directions. Thanks. The light bulb, for example. Which direction is the light traveling? Well, it's traveling in all directions. Does that make sense? Energy doesn't travel just one way, it travels all ways. All ways. Same thing with sound. I'm currently speaking. That's a form of energy. That energy is traveling that way, that way, that way. Someone behind me should be able to hear. Does that make sense? So that's a scalar. Based on that, it's kind of hard to attach a direction to different forms of energy, and especially when you're talking about heat, because heat is the form of energy we're really going to focus on in the thermal unit. Same concept. Let's say there's a fire, a campfire that you're sitting around. Does the heat from the campfire go just one direction? No, I mean, that's why we usually sit in a circle around a campfire, right? Because it's going to heat you up from all directions. Does that make sense? So the unit of measurement is a joule for energy, but energy can have so many different forms that it's actually very difficult to directly measure energy. So in chemistry, we indirectly measure energy using a different tool. Does anybody have any idea what the main tool we use to measure heat? Thermometer, yeah, but here's the problem. What does a thermometer measure things in terms of units? Degrees Celsius, or it's probably better if we convert things to kelvins sometimes. You guys remember kelvins? The idea that basically you subtract 273 or add 273 and make an absolute zero. Long story short, though, energy is different than temperature. Does that make sense? So if we want to measure and quantify an amount of energy, we can kind of do that, but we have to measure temperature. And so I can now finally start talking about my slide here. I don't even know when someone figured this out, but they basically came up with a device, and we call it a calorimeter. And the field is called calorimetry, hence the title. So I just want to show you guys two very basic calorimeters. This is one of my better ones. I mean, it's not overly expensive, and honestly, it's not that technologically crazy. I mean, basically, there's a plastic lid, and there's a hole inside here for you to put a thermometer. Does a thermometer measure energy though? Not directly. Well, I'll show you how to solve that problem in a bit. Okay. But indirectly, it can measure energy through the form of temperature. Okay. Here's the problem though. I just mentioned energy travels out in all directions. So let's say that there was a campfire. Say the campfire is in this bin right here. Put the thermometer right here. Is that measuring all of the energy the campfire is getting off? No. It's probably not, right? Because the energy, sure, it's coming this way towards me, but the energy is going in all directions. Make sense? I could be really brave and stick my thermometer right in the middle of the fire. No, that works. Well, that's basically what this thing tries to do here. It's an insulated container where there's like all these different components to it. Basically, it's just trying to insulate stuff. We put some foam inside, we put another container inside, and let's put that upside down. Now what we're trying to do is we're trying to create an isolated system. Do you guys recognize the word isolated versus closed system? An isolated system would mean that no energy, if at all possible, is lost. Right? So what you do is you basically, whatever chemical reaction is happening, you try to put it inside the middle of this calorimeter here. Right? And let's say there's a little mini explosion or some sort of endo or exothermic reaction inside there. What's going to happen to the energy? Well, hopefully it will be contained inside the little container. Does that make sense? Is this foolproof? Well, this one's not because, I mean, there's a hole in the top. So Will some energy possibly be able to escape? Yes, some. But do you guys get the basic concept? You're trying to create some sort of device where the reaction that creates or uses energy is stored internally. And so when it permeates out in all directions, hopefully it's insulated on all the different sides. But obviously the top side is not as insulated. I have a few of these, but sometimes in the lab we just use really basic ones like this, where all it really is like a beer can cozy. Styrofoam cup, a little bit of a lid on it, and same concept, just take your thermometer, put it inside, and hopefully when something is exothermic, all of the energy will stay inside there and it won't be able to escape. Does that make sense? So that's at its core what a calorimeter looks like. Okay, so I just got a basic picture here. In terms of highlighting important stuff, basically what you're looking at is some polystyrene cups, like styrofoam, a thermometer, and we use one more thing in most of our labs. We use water. Almost all of our calorimeters involve water. Let's say I was trying to measure the fire, a campfire. There's a campfire in the bin there. Is it reasonable for me to put the thermometer directly into the fire? Probably not. One of the biggest reasons is that if I put the thermometer in the fire might actually damage the thermometer. Does that make sense? So a smart scientist wouldn't want to directly put his measurement tools in harm's way. Again, if we're talking exothermic reactions, it's very likely you'd ruin your thermometer. So what we do instead is we put the thermometer inside water. The reason being is that water is able to hold a lot of energy without too much problem. Does that make sense? Like we can boil water, we can add energy to water. Water will be able to store that energy for us. We'll then put the thermometer in the water and measure the water. This becomes a bit of an issue because, well, now we're talking about not directly measuring things. First of all, we're using a thermometer. That doesn't even measure energy, it measures temperature. And then we're not even measuring the reaction itself, we're measuring some water nearby the reaction. Does that make sense? So it's not perfect, but in an ideal world, hopefully this will help us find a way of measuring how much energy there is. So let me just read the things off the slide here. The idea here would be that whatever energy is either gained or lost by the chemical system should be like isolated and contained. I think this is the key word here. If some energy is gained by something, it needs to be lost by something else. Or if something else loses energy, it should be gained by something else. Does that make sense? That's like my golden rule down at the bottom here. Ideally, energy should be conserved. So, I don't want to put this here. Let's say that, again, we have a campfire right here. I'm not going to put my thermometer directly in the campfire. But what I am going to do is I'm going to put my calorimeter near the campfire instead, with my thermometer inside. The idea would hopefully be that all of the energy from the campfire ends up inside my calorimeter. That's the hope. Will that happen? Will all of the energy from my campfire end up inside there? Probably not. Does that make sense? So for that's what we're ideally going for here. Okay, just a picture basically. I guess I can look at that. Maybe graphically, this is a good way of approaching it. You guys are for sure on your diploma and on my test, you're going to see a lot of graphs trying to illustrate kind of how things would, I don't know, look in a pictorial format. Let's say that you had some zinc and some hydrochloric acid. Do you guys know what happens when you add zinc and hydrochloric acid? What was that? It makes hydrogen gas and zinc chloride. If I haven't shown you this before, I probably will at some point in this year. Basically, it causes it to bubble, and the zinc will like fizz and buzz all the way around the hydrochloric acid. It's exothermic. Okay. Well, if zinc and HCl, if it is exothermic, does that make sense then why this graph goes down? Because what does an exothermic reaction do? It gives off energy. And so the zinc and the hydrochloric acid are going to give away their energy, which is why this graph goes down. Well, where the heck does that energy go? Is it just lost? Well, ideally, if we have some sort of calorimeter device, that device will then be able to measure that energy as something else increases. So imagine that it's in water. You put a temp thermometer in water. What you'd hopefully discover is that your water will now increase in energy. And what we're going to do is we're going to measure it as like a temperature change. So as the chemical reaction gives away its energy, we'll notice that the water that it's in will go up in energy. And hopefully, however much one goes down, the other one goes up by. Does that make sense? Okay, now for the core problem though. A thermometer measures something in degrees Celsius, and we know that energy is measured in joules. We need a correlation. So here's the first formula that I need you guys to write down. And this is the sucky news. You have to either memorize this, or at least at first you have to write it down in your data booklet. But they don't give you this formula on the diploma. So write this one down. The formula to convert is usually written like this. Q equals MC delta T. You may even already have that written in your formula book because I give you the ones from the kids who did the diploma last year. Maybe they already wrote it in there. It's already in there. Okay, so this formula converts energy and temperature to each other. But it actually requires two other values. There's actually 4 variables in this. Okay, so first thing we do is for energy, often energy is written with an E. That's a standard convention. But for whatever reason, in this formula here, we change energy out for the letter Q. I do not know for the life of me why they picked Q, but just go with it. So Q stands for energy. Very specifically, it's trying to measure how much heat energy something is producing. Okay. M depends on mass. And I've got to be really specific though. M depends on the mass of the water inside the calorimeter. I'm going to present an analogy here. Let's say that this was the calorimeter that was somehow measuring a reaction and there was a little bit of water inside, like just however much this little beaker could hold. And let's say that we heated it up. And let's say a second calorimeter, only that calorimeter was the size of a bathtub. Which one would have more of a temperature increase? The little amount of water or the big amount of water? Which one would have more temperature increase? The little one. Does that make intuitive sense? The smaller the mass of the water that is being heated up, the more the temperature increase. Let me say that one more time. The smaller the mass of the water being heated up, the larger the temperature increase. Basically, if you increase the amount of water you have, that would decrease the amount of temperature change. Or if you were to decrease the amount of water you have, that would increase the amount of temperature change you have. So those things they have an inverse relationship. As one goes up, the other goes down. I would think most of you guys intuitively knew this. If you were to take 2 pots of water because you wanted to boil them to make spaghetti, and you put it on the stove, and both burners were at the same amount of heat, but one of the pots was really, 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 really big, like massive, massive pot, and then the other pot was just a little pot. Which one would boil first? The little pot would boil first. Doesn't that intuitively make sense? So that's one of the factors, the mass, but let me be specific. This is the mass of the water being heated. The other thing is a constant. It's called the specific heat capacity. You find all of these constants in your data booklet, actually. Let's go Brad's here. You guys can flip open to the second page. There's a chart of stuff that's miscellaneous. Can you guys find that chart? Specific heat capacities are represented by the letter C. And basically the concept is the bigger the specific heat capacity, the more energy something can absorb before it gets hot. Let me say that one more time. You may even want to write that next to it. The bigger the specific heat capacity, the more energy something can absorb before it heats up. The bigger the specific heat capacity, the more energy it can absorb before it gets hot. Okay, imagine you're back in the kitchen and you've got 2 big pots of water. And in each of those big pots of water, you put in 2 different spoons. One of the spoons you put in is a wooden spoon. And the other spoon you put in is made purely of metal. Which one heats up faster? The metal. Does that make sense? The reason why, say both of the spoons have the exact same mass. Metal just has the ability, naturally, to absorb and transfer heat better than, say, a plastic or a wood does. Does that make sense? So things on this list that have low specific heat capacities, they will get hot very quickly. So what is on this list again? You've got your tin, your iron. You guys have to see like how tin and iron are very low numbers. 0.277, 0.499. Water is actually one of the highest specific heat capacities. Water can absorb a lot of energy before it actually heats up, which is actually the reason why we use water to cook our food. Because there's a lot of energy in the water that we use to, like, say, boil spaghetti noodles with, but the temperature only gets as high as 100 degrees Celsius. So the temperature is limited, but there's still lots of energy in that water. That makes sense? Okay, long story short, because I'm rambling like I always do, all 4 of these things then go together in one big formula. Q is how much energy you get, M, mass of the water you use, C, the specific heat capacity. Usually it's of water, but I've seen them throw in some weird questions in the past on diplomas where they make it not be water. And T is how much temperature change there is. So let's try some examples. Let's say that you want to figure out how much thermal energy has been released if some water ends up going from 20 degrees Celsius to basically 100. So water has undergone basically, 80 degrees or so temperature change. We want to figure out how much heat there's been. There's one more thing I need to let you guys know about. That's not a mass. Because what's mass measured in? Okay, this is a volume. But this is so convenient. For water, this is only for water, the density is 1 gram per 1 milliliter. Water, if you have a milliliter of it, just so happens that it weighs a gram. It's the only thing in the world that would do that. If you had a milliliter of lead, it wouldn't weigh a gram. If you had a milliliter of air, it wouldn't weigh a gram. But water, this is just beautiful how it just works out. If you have 1 milliliter of water, you have 1 gram of water.
So if you ever get a milliliter value, it's automatic.
That's exactly what I'm going for, yeah. So what they might do to try to mess with you on a diploma question is rather than give you a mass of something, Q equals MC delta T, you need a mass. If they give you a volume, so long as that volume is water, you have the same thing. So let's try it. The formula Q equals MC delta T. Rather than mass, we have volume, but that's good. So we can say 115 grams of water is what's getting heated up. Then we need to know that C value for water, which is a constant. And you'll probably memorize this over the next little while. It's 4.19. And I've said this many times before. I'm a big believer, write in units. I think it helps. So the units for a constant are joules divided by degrees Celsius and divided by grams. Both Celsius and grams goes on the bottom of the fraction. It doesn't matter which one's first. Last thing, you need to do delta T. Are you guys aware of what the triangle means? Change in, okay, so you just need to find the difference in the temperature, which looks like it's roughly 80-ish degrees. Does anybody have the exact number though? Cool, thank you. Degrees Celsius will cancel, grams will cancel, and we'll have an answer. We just need to grab a calculator. I need one. $79.2, you said? Okay, so I got 38,162. Okay, more subtle thoughts about how, when you eventually write a diploma, they're going to try to trick you. Units is probably one of the most common ways they're going to deal with this. The unit for this is going to be in joules. However, based on your sig digs, you're only allowed to have 3 sig digs. Because this has 3 digits, this has 3 digits, that has 3 digits. So you only get 3 digits. So one of the ways they might try to mess with you is they might write it like this. 3.82 times 10 to the 4 joules. That's one way they might deal with that. So be okay with how I converted that? Here's the other way they might do it.
Mr. Laborado, please dial 103.
It's probably more likely they'll convert it to kilojoules. So a kilo is 1,000 of something. So if you pull back the decimal place 1, 2, 3 times, they might write it as 38.2 kilojoules. Does that make sense? So quick recap here. All reactions are endo or exothermic. I can't put a thermometer directly into the fire. That's not going to work. But what I can do is I can put a boiling pot of water right into the fire and put a thermometer inside that boiling pot of water. Does that make sense? If I measure the temperature change of that water, I'm going to make an assumption that all of the energy that the fire has goes into the pot of water. That assumption is probably not true, but we're going to do our best to make sure that that's the case. If we then know the mass of the water that's being heated up, if we know the capacity of the water to maintain heat, and if we can measure temperature, that's enough to then find out how much energy change there is. So at its core, this is kind of where our unit starts, trying to determine how much energy there is. Okay, why don't I do a couple more slides and we'll take a break, because I've got so much to start with, obviously. Sorry, I'll probably be talking most of the class. Q is a letter that, for some reason, has been arbitrarily assigned to be heat. But is heat the only sort of energy that a fire might give off? You'd probably argue that there's lots of heat, but there's also light, sound perhaps. Maybe even you could find a way to suggest there's some kinetic energy being given off as like stuff like sparks. You ever have like a little ash kind of come out of the fire and land on your jeans and you just brush it away? Right. So is the only form of energy that exists heat? I'd say no, probably not. So we have a different word to describe an all-encompassing, like all forms of energy, and that word is called enthalpy. Basically all kinetic, all potential, basically all energy that could exist, we call that enthalpy, just an all-encompassing word. And sometimes we use that word as well. Down here I have like a little formula. We like to think that heat is the only form of energy that exists. Again, that assumption fails though, because not all of the energy something that gives off is going to be heat. But we like to assume that it basically is. So one of the notations I need you guys to be familiar with is delta H notation, which basically just means the change in energies. Energy is going to be lost due to light, energy is going to be lost due to heat, lost due to sound, or possibly gained. Just in case you're not aware of how the triangle works, but I think you guys seem to be familiar. Basically, if you want to calculate a delta H, a change in energy, you need to know how much energy the final thing has, you need to know how much energy the initial thing has, and then subtract the two. I want to go back to my first slide, and then we'll take a break here. I think this is a good slide to go back to now. Here is your final amount of energy. Here was your start amount of energy. If I gave you a graph and I say that it started off with 800 and it ended up at 100, how much energy was lost? 700. Does that make sense? From 800 down to 100 means that this exothermic reaction would have lost 700 joules. But does the fire really lose that energy? Well, the energy just goes out to the surroundings, and so something else would have to gain that energy. And so therefore the water would have to gain 700 joules of energy and heat up instead. Does that make sense so far? Okay, cool. Take a 5-minute break, because I'm going to be talking for the next half hour still. And we'll keep going. Wait, so while you guys were gone, I set up just a basic experiment to kind of describe what our next slide is. And this is probably a good time to talk about our lab tomorrow. I'll get to that in a second here. Let's try the example here. Imagine that I've got a candle sitting underneath the tin can. The tin can, by the way, I filled with water, and there's a thermometer inside. So let's go through why I did all that stuff. Why is there water inside the tin can? Well, if I want to measure how much heat the candle is giving off, it's probably not that smart to just stick the thermometer inside the flame of the candle. Does that make sense? Like, it's not the most efficient way of doing that. It's going to ruin my thermometer. So I will heat up this water instead. Here's our first problem. Is this a very effective calorimeter? Is all of the heat from the candle going inside that water? No. I would say that, I mean, hopefully most of it is. Well, but some of the heat is going to be inside the tin can. Some of the heat is just going to go off to the surroundings. That's why this device is a little bit better. This one is sometimes called a bomb calorimeter, because what they do is they put the explosion or the candle inside, and they have it explode from the inside and try to keep everything contained. Does that make sense? If I could somehow make this thing big enough to put a candle and a whole bunch of stuff inside here and then close it off, hopefully that would then make it so that I don't lose energy. But ideally, all of the energy from the candle makes it into the water. Pause for a second. Anybody want breakfast?
I heard candle and water.
Yeah, we're doing an experiment. Just a demo. Anybody hungry?
Why are you melting wax?
We're seeing how much energy it gives off.
No one?
Thank you, though. Okay, let's talk a bit here about the candle. Is the candle, I think I'm giving away the answer here. The candle is exothermic. Does that make sense? The candle itself is giving away its heat. And ideally that heat should end up in the water that's measured right here. So now let's do the example on the board here. First thing we got to know is how much water did you put inside the can? So I just put a random amount of water, but let's say there's 100 milliliters inside the can. Let's say that it goes up by that temperature change. Could you guys then figure out how much energy change, which we now call enthalpy, the candle must be losing? Because the candle, by the way, is going to be going down and down and down in size. The reason why the candle is going down in size is it is losing its energy. Does that make sense? So you guys try this one. See if you can beat me to it. So you could write it as Q equals MC delta T if you wanted to. Sometimes we say that Q is equal to delta H. Both of those are considered acceptable. Maybe let's get this. Is that the final right answer?
No.
I got to round to sig digs. Okay, now this is dicey here. This and this look like they have 3 sig digs. They don't. Because when you subtract them, the actual temperature change only had 2 sig digs. So based on the temperature change only being of 8.8 degrees Celsius, I would call this 3.7 kilojoules. Okay, this is another good teaching moment here. Because this was called the enthalpy change, this would actually still be wrong. We're not quite there yet. It's a minor detail, but the correct answer would be negative 3.7 kilojoules. Anyone want to hazard a guess as to why it's negative? Yeah. The candle itself is the source of the energy. And that candle is losing its energy. Does that make sense? And because it's losing its energy, it's got to be a negative. If you go back to that one graph that I was referencing earlier here, it used to have, 800 energies. I don't know, 800 kilojoules, whatever. And now it's down to 100 kilojoules left. I mean, that candle right there used to be this tall, and after it burns, there's less. Does that make sense? So, long story short, if something loses energy, and we talk about it in terms of enthalpy, they're probably going to expect that you throw a negative on for things that lose energy, and throw a positive on for anything that's endothermic that gains energy. Does that make sense? Okay. While I've got the demo out here, why don't I talk about tomorrow's lab then? Tomorrow, what we're going to do is we're going to grab one of my boxes of cereal, and I'll probably have you do 2 or 3 different boxes. And the first thing you're going to want to do is go to the back of the box, and you know where they put the nutritional information? Well, it claims here that there's 100 calories in Cheerios. Okay. A calorie is another unit of energy, and there's a simple conversion which I list somewhere in the lab that converts calories to kilojoules. So what we're going to do is we're going to see whether the food itself actually contains 100 calories. But here's the problem though. How much cereal should I burn? Well, the back of the box will say that it's 100 calories per 27 grams. Does that make sense? Just the raw amount of energy is not sometimes useful. Sometimes it depends on how much is actually burned in grams. That candle right there, if I use the candle for 5 minutes, it would burn off, that much candle. If I burned the candle for an hour, it'd probably run through the whole candle. Does that make sense? Which one would cause the temperature to go up more? Well, if I let the candle burn for longer, the temperature would go up more, right? Doesn't that make intuitive sense? So sometimes what we need to do is we need to calculate an enthalpy per unit used. So one more time. Sometimes we have to calculate an enthalpy in kilojoules per unit used. Now the box, the cereal box, measures it per gram. That's a unit of measurement. But what do we usually measure things in the chemistry lab? Do we measure them in grams? Or what's another measurement we use that's similar to grams, but just 1 molar mass different? Moles. Does that make sense? So what I want to go to in my next couple of slides here is talking about how we can find a kilojoule number, and that's fine, that's great, but sometimes a more important number is a kilojoule per mole number, where we figure out how much energy you get per amount of stuff you use. Does that make sense? This is where, like, say, dynamite is particularly explosive, because dynamite gives off a lot of kilojoules, but it's per a small amount. Does that make sense? C4 is even better. You'd probably get just as much energy from C4, but you're only using, like, a small little brick of it. Does that make sense? So. Okay, just a slide just to talk quickly about the idea of positives and negatives, though. If you're talking about enthalpy, negative means it's exothermic, positive means it's endothermic. The negative positive signs are important. They'll try to trick you up on that on diploma questions. You know what? In the interest of time, let me skip this one here. No, I shouldn't. Okay, no, we're gonna do this one. I should talk about this one. Okay, let's say you take some hydrochloric acid and you neutralize it with some sodium hydroxide. We want to try to figure out the enthalpy change that occurs. To figure out enthalpy change, that's like your delta H. As you look at the thermometer readings, if the temperature goes up, was it an endo or exothermic reaction? Exothermic reaction. When we're done then, make sure to throw in a negative. Does that make sense? So Your change in enthalpy is really the amount of heat you get. That's mc delta T. Where's the mass coming from in a question like this? Yes. Yeah, both of these are aqueous solutions. Hydrochloric acid is aqueous, which means that it's mostly water. And same thing with sodium hydroxide. It's an aqueous solution. Also, it's mostly water. So when you want your mass, it's going to be 125 grams because that's 75 plus 50. So I figured I should talk about this twist. Does that 1.0 moles per liter, is it going to factor in? It won't, by the way. It was just extra information on this question. What should we use for the C value then? Well, I mean, if hydrochloric acid is aqueous and sodium hydroxide is aqueous, they're essentially made with water. Yeah. So the C value we can use is water. And then you just need that temperature change of 5.6 degrees. So you guys can calculate that. That's the only twist I just wanted to point out here is that if you take two chemicals and you pour them together, the mass you would use is their combined mass, or in this case, I guess it's a volume. 2933. So that's going to be 2.9 kilojoules. Negative. Anybody else got that? I'm just cheating off of Brad here.
Yeah.
Okay, cool. Okay, so this is where I was trying to get to, I guess. Kind of got distracted here. Enthalpy of a reaction is just how much energy there is. But we may want to consider how much energy you get per amount burned. If I burn 1 gram or if I burn 100 grams, there's going to be a difference there. Does that make sense? If we, in tomorrow's lab, if I have you guys burn 27 grams of Cheerios or 5,000 grams of Cheerios, which one's going to make a bigger fire? The 5,000 grams of Cheerios would make a way bigger fire. Does that make sense? So basically what we need to do is just divide by moles. That's all. So sometimes it's written, I pulled this out of your textbook. It's so confusing at first. How can I make this simple? Okay, let's say I write this, delta H with a C right here. What this notation right here would mean is we want to know the change in enthalpy, how much energy change there is, and this C right here would imply that it was a combustion reaction. That makes sense? This number right here, the unit, would just be kilojoules. Because I'm just telling you just how much raw energy this would provide. If I did a delta D with an H, this would tell you how much energy change something that decomposed gives off. So the little letter that comes between the triangle and the H, this letter tells you what type of reaction it is. And if we don't happen to know whether it's decomposition or combustion or whatever it happens to be, sometimes we write an R in that spot, which is what I have right here. If you ever see like a delta RH, that just implies that this is the energy that a reaction, R for reaction, would give off. Does that make sense? Okay. But if you throw a little m afterwards, if you did delta RHM, this is now the enthalpy change in kilojoules per mole. So that little m afterwards is now a ratio number, letting you know how much energy you get per unit of stuff consumed. Does that make sense? Let me just try a couple examples just to make sure I didn't lose you, because I pulled this right out of the textbook, and I think it's confusing. So let's say I told you this. Delta CHM equals negative 100 kilojoules per mole. What does that mean in the notation? Here's what it means. It means that you combusted something. Something blew up. In blowing up, it gave off 100 kilojoules of energy. But not just 100 kilojoules total, it gave off 100 kilojoules per mole that you blew up. We don't actually know how many grams you used, but we know that this is how much you get per mole. Does that make sense? If I told you delta FH equals plus 50 kilojoules, this would mean that there was a formation reaction happening. Now, we don't know how much per mole it happens to be, but we know that the energy went up by 50 kilojoules, meaning it was an endothermic reaction. Does that work? Okay. So let's do an example. I want you guys to calculate how much enthalpy, how much energy change you'd have if you combusted 10 grams of propane. And this is really frustrating at first because you look at this question and you go, where's all the numbers? Anybody else have that thought? Where you go? So let's start with what we have. I actually do this on purpose. So, you have 10 grams. Let's start with that. Okay, in chemistry, do we normally work with grams? Is that like the preferred unit of measurement? Usually like moles, right? So how do you convert to moles? Divide by molar mass. Okay, so let's start with that. So if you want to write out what I'm doing here, I'm dividing by molar mass. Whose molar mass do I use? Anybody know what propane is? Fair enough. If you're really stuck and you have your data booklet, there is a list, one more page over, of a whole bunch of compounds, and it lists up top in the corner there, it says delta FH, and it gives a whole bunch of numbers. Okay. Now the delta FH, what does an F mean? Formation. Are we undergoing a formation reaction here? If it were a formation reaction, by the way, we could just use these numbers. Because you know how when I first pointed out that we seems like we're lacking a number? Guess where those numbers are going to show up from? Does that make sense? The only downside, though, is that these ones only work for formation. So I'm going to cheat to get around that in a second. But also, if you're stuck on what propane is, though, you should be able to find it on the list, I'm sure, right? So can you guys find propane on the list? Okay, so propane is C3H8. So we need a molar mass for propane. (1201 times 3 plus 101 times 8. I got 4411. I'm not going to type that in my calculator yet. This has now given me, if I were to type this in, grams would cancel. It gives me moles. What am I looking for, though? Change in enthalpy. What's enthalpy measured in? Well, enthalpy on its own is just going to be joules. Probably it's actually going to be kilojoules. So we're going to want to find a number that gives me kilojoules. But we don't want it to be per mole. Well, we don't want that mole anymore there. So we need to find, I'm just going to write this out here. We need to find a kilojoules per mole ratio. Now, I just said this a second ago here. In your data booklet, these numbers right here are all molar enthalpies. See how it says there these are units of kilojoules per mole? The only downside is these are for formation reactions. So if it ever feels like you're lacking information in a question, chances are it comes out of your data booklet. But the point I want to make here, though, is that those are formation reaction numbers. This was a combustion reaction number, so we can't use our data booklet. Fair enough? So I'm only going to do this just for the first example, just to point this out. But if you needed this information, you could just Google it. Honestly, it's actually really easy to find. I would look for like the molar enthalpy of combustion for propane. And these numbers are usually found. I've ever shown you guys my big CRC handbook. Like this thing right here basically has all sorts of just numbers of like constants for things. So if you're not told a number like that, we would just look it up somewhere. You guys see where it would be here? See this notation right here? Delta C. So this is now a combustion number. They really should have put an M afterwards here. That's probably standard convention, but I guess they didn't here. But here's the number we need. Negative 2202.0. That's how many kilojoules per mole you get. Does that make sense? So 2202.0 kilojoules per mole. So if you're lacking this number, you might need to Google it on the internet, but on a diploma, it'll be in your data booklet, and it'll for sure be a formation reaction. Does that make sense? Why was this number that I Googled on the internet, why is it negative? Yeah, what do combustion reactions do? Yeah, they blow up and give off heat. Does that make sense? So now what I usually suggest to do is I don't put the negative in until I'm done. So I'm just going to now type all this in my calculator and take 10 divided by 4411 times by 2202.0. I got an answer of 499. The unit for that would be kilojoules. And now that I'm done, I'm just going to use common sense and say this is an exothermic reaction. It's giving off energy, so it needs to be negative. That makes sense? Okay, so I just did one. Why don't you guys try the next one here? The big difference between the first one and the second one is this time, rather than making you Google the molar enthalpy, I tell you the number. So why don't you guys try the second one, see if you can replicate it. So find butane, 10 grams. The number in your data booklet, if you needed to, you'd use it. The only problem is those are formation numbers, so that doesn't help us yet. But I do tell you the combustion number. So. Anybody else get this? Details are important. Don't forget the negative. The negative is what implies that it's exothermic and giving off energy. And the kilojoules are important as well, just because that's the unit of measurement we're working with. Does that make sense? Okay. Here's a slide where I basically am just reiterating the point that the enthalpy change, we assume that it's all heat. And that's in a lot of cases, I mean, you guys have heard the acronym about assuming things, I'm sure. We'd like to hope that when that candle was burning, all of the energy was heat. But it's not, right? Some of it's light, some of it's sound. But that's the hope, is that whatever energy change you have is heat. This is another piece I pulled out of the textbook right here. What we can do sometimes is combine these two concepts and put them together. Okay. Delta H is really a kilojoules amount, and we can calculate a kilojoules amount by taking a mole number and timesing by a kilojoule per mole number. That's basically what we just did in the last slide. But another way that we can calculate heat is using the MC delta T stuff that I started class with. And so this is like culminating, this is like putting all of it together in like one big super formula. So let me try an example. There's a lot here. Okay, I'll give you a little blurb about ethanol. Ethanol is added to gasoline, it makes something called gasohol, and then here's our important stuff. What we're going to do is we're going to take 3.5 grams of ethanol and we're going to blow it up. In doing so, it causes the water of 3.63 liters to increase, and we're going to try to find the molar enthalpy of combustion for ethanol. Okay, so scenario, just to make sure we're clear. This water right here in the tin can, 3.63 liters. The temperature that we measured, about 7 degrees change. And the stuff underneath that we burned, we actually measured how much of it we burned, because that matters, right? How much is burned, and we burned 3.5 grams. So now I want to put this all together. I find that at least to start with, a lot of kids like using this formula right here, which is, it's kind of gross at first, don't get me wrong, like it's ugly, but write it out something like this. M delta C HM equals MC delta T. Okay, let's talk about what everything means again. Let's start on this side. This is either side. What's that delta T? Do we have a change in temperature? Anybody calculated? It was like 6 something degrees, right? How much? 6.3? Okay. All right, what's C stand for? Of what? Of water, yeah. Because water is what was, like, we didn't put the thermometer directly inside the explosion. We put the thermometer inside some water and the water by the explosion. So that's 4.19 joules per gram degree Celsius. What is M? Good. Now you gotta be really specific. Sean's got it right. It's the mass of water. Because if you look at the question on the slide that we've got right here, see how there's a mass right here of ethanol? That's not the mass we use. Does that make sense? So make sure you're very careful. It's not the 3.50 grams. It's the mass of water that goes here. How much water did we use?
6.63, which is
3.63 liters.
Yeah, but then
Okay, so yeah, convert it to milliliters. It's 6.3, that number. That's that many milliliters. And that's how many grams there is. So there's 3630 grams. Sorry, I really shouldn't have put this on 2 slides like this. 3630 grams. Make sure you're very clear. This number has to be for water, not the actual mass of the stuff that's blowing up. All right, all of this right here is just one thing. It's very complicated because there's a lot of subscripts in it. What does the delta mean? It means change. What does the C mean? Is the C appropriate? Yeah, we blew up ethanol, so the C is appropriate. Okay. The H refers to the fact that there's an energy change. We call it enthalpy change. And the M just means that by the time we're done, it's now per mole. It's the molar enthalpy. So this is actually what we're looking for. This as one big thing is the variable we're solving for. So I mean, I'm just going to rewrite it as it is here. This is the variable we're solving for. The last thing we need then is how many moles of the stuff we were actually blowing up. How do I calculate how many moles of the stuff we actually blew up?
just take the mass of it, get more mass.
There you go, mass divided by molar mass. So this guy right here, it said that it was 3.5 grams. And we're going to need to divide by the molar mass of ethanol. Anybody know what ethanol is? Did I give the formula somewhere nearby? That'll work. Okay. so 1201 times 2 plus 101 times 6, I guess, plus 16. I got 4608. Okay. We now have everything kind of set up where we need it to be. Now I'm going to cancel a crap load of units. So this is a degree Celsius over here. That'll cancel that degree Celsius over here. This is a gram right here. It'll cancel that gram right here. I'm left with joules. That's okay. I can live with that. Over here, what happens on this side in terms of units? This grams cancels and this grams cancels. And I'm left with moles. But I'd like to isolate for that thing right there. Good. So maybe I can do that all in one step. Let's take the 3.5 grams and the mole for the 46.08. Cancel that out. Long story short, what you have to type in your calculator is, I'll even do it up on the calculator for you just to make sure you can see it all. We need 3630 times by 4.19 times by 6.3. This first half right here is just how much energy change there was. Now I'm going to divide it by how many moles I actually burned. Did I burn through a full candle, or did I just burn through a part of a candle? Does that make sense? But to calculate the moles that we use, we need to take our mass and divide by our molar mass. And if I do that, I get this big number. That should be sufficient for now. Anybody else get that? Okay. What units is this? Well, in terms of what I haven't canceled, there's a joules number left and a mole number left. Now, a couple of thoughts here. Normally, we don't work with joules per mole. We work with kilojoules per mole. So that's probably the first thing we should do is divide by 1,000 and make it back to kilojoules per mole. So now it's 1261 kilojoules per mole. Okay. And one more thing, we should throw a negative on. Why should I throw a negative on? Yeah, because it's releasing energy. We intuitively should know that because it's combustion, it blows up, it gives off energy. Technically, I should do sig digs as well. 2 sig digs? 3 sig digs. Ooh, good catch. 6.3 is only 2. So probably the most appropriate way of calling this would be to make it 1.3 times 10 to the 3 kilojoules per mole negative. And we would notate it by this. Delta H with a C between there and an M. This means that the energy change that's going to occur in a combustion reaction per amount of stuff we use is going to be basically 1260, 1.3 times 10 to the minus 3. Negative because it's giving off that energy. How'd I do? You follow that? I would say that in a way I've taught you 2 different things. Well, 2 main formulas. There's the Q equals MC delta T formula. That will give you an energy amount. But there's also the idea of being able to take like a moles and a mass and a kilojoules per mole and put all that together as well. Combining those 2 things into one super big formula, what we can really do to calculate a kilojoules per mole number is we can find a mass of water, a constant for water, a temperature change, and divide by how much stuff you burn. And that's what we're going to do tomorrow. In tomorrow's lab, you guys are going to measure how much water you put in the tin can. You're going to use a thermometer to figure out how much temperature change there is. And then underneath, rather than putting a candle, you guys are going to put some cereal. But before you put the cereal down there, you should weigh it. Because what we're going to do is we're going to weigh the amount of cereal you have when you start. Then you're going to burn all of the cereal to the best of your ability. What's going to happen is not all the cereal is going to disintegrate. Like there's going to be some charred remains left. So then we're going to weigh the remaining cereal that's left over. Does that make sense? The difference in that mass will be how much cereal was burned. And that'll be the mass that goes on the 3.5 grams. And then we can calculate that number. So if you were wondering where the heck all these numbers in your data booklet come from, it's by doing a calculation like this. That makes sense? Is that my last one? Do I have anything else? Big summer sled. Okay, questions, comments, concerns, conundrums, curiosities, complaints, criticisms, critiques, queries. I'm running out of C keywords. How are you guys feeling after kind of our first big day? Yeah, there's a lot, eh? Okay. If you're freaking out a little bit, please give me a little while to help reinforce this point. That's one of the reasons why I want to do a lab literally like the third day into the school year, because I think it helps when we actually get to do an experiment and kind of see how this all fits together. So here's what I need from you guys. Tomorrow, make sure that you have the lab printed off. You guys should know the drill. You can work. I don't mind if you work in a larger group, but I want you to hand in a lab with either one person or two people. Okay. I have some cereal that you guys can use, but if you'd like to, and you want to bring your own, like a little baggie of cereal just to test and see like what corn flakes are like or what Apple Jacks are like. If you want to bring your own cereal to burn just to see, that's fine. But basically tomorrow we're going to test 3 different types of cereal and see how much energy they have. Does that make sense? All right, cool. One last thought, then you guys can go. If you have that form that Jessica looks like she's got signed here, can you guys make sure you get those signed ASAP so that I can actually legitimately say you guys can go? Okay. Fair enough. All right, so get me this as soon as possible. Otherwise, you guys can take off. And I'll make sure I post this video in case you guys want to watch it again.